Welcome to the Deep Dive, where we piece together insights from your sources to get you well-informed fast. Today, we're tackling something huge. We're going to assemble this incredible puzzle, the history of the computer. Just think about that device you're listening on right now. It wasn't just one person's idea, was it? It's really the result of almost, 5,000 years of people building on each other's work, collective genius.
Exactly. And that's our mission for this deep dive, really. To appreciate just how fast technology moves, but also, crucially, to see how all these different people, different groups over centuries, each added a vital bit or piece, hardware, software, all coming together to give us these incredibly powerful machines we use every day. We're basically tracing this long, winding path from really ancient tools right up to the supercomputer probably sitting in your pocket.
Okay, so if we want to really get this, we need to go way back to the very beginning. Our story kicks off not in some, modern lab, but way, way back, around 3000 BC. With the Chinese abacus, it's kind of hard to wrap your head around, but this simple frame with beads, it really set the stage. One of the first actual machines humans made just for counting and calculating.
And what's really interesting, even back then, is how quickly these early ideas sparked reactions. So fast forward quite a bit to 1642. The abacus idea evolves into the Pascaline, invented by Blaise Pascal, brilliant mathematician, scientist, first mechanical adding machine. And right away, you see the first hints of, what we'd now call technophobia. Mathematicians at the time were actually worried they'd lose their jobs because of this new machine.
That is striking, isn't it? It sounds so much like the conversations we have now about AI and jobs. Do you think that underlying fear is basically the same, or is it just the speed and scale today that feels different?
Oh, it definitely echoes. I mean, the fear that a machine might replace you, that's ancient. Whether it's a mechanical calculator or, a smart algorithm, maybe the difference today is just the sheer speed, the exponential curve, and how AI can touch almost any field. But that core anxiety, will this thing do my job better?
Yeah.
Yeah, that's been around for ages.
So even with those worries, the innovation just kept rolling. From the 1660s into the early 1700s, we get Gottfried Leibniz. This guy was involved in so many fields, often called the first real computer scientist. He was inspired by Pascal, built his own calculator, but his was a big step up. It can do all four basic arithmetic operations, adding, subtracting, multiplying, dividing.
And here's the really crucial bit. Leibniz was the first to properly lay out the concept of binary arithmetic. Just think about that. Reducing everything down to SOs and ones, on or off. It seems abstract, but that became the absolute foundation for how all our technology communicates today. It's a language of switches. It was this conceptual breakthrough that made everything else possible, digitally speaking.
Okay, so we've got basic calculation, we've got binary. The core ideas are there. Then the 1800s arrive, and things get really interesting. It's not just about calculating anymore. Now we're talking programmability. And that brings us to Charles Babbage, often called the father of the computer. Around 1820, he figures out something key. He realized that lots of complex calculations just involve repeating the same simple steps over and over, steps that could be automated.
Exactly.
Yeah.
And that led him to design his first machine, the difference engine. The idea was it would be totally automatic, run by steam power, follow a fixed set of instructions, and print out the results. But then around 1830, he shifted gears to something way more ambitious. The analytical engine.
Right, the analytical engine.
Right.
This feels like the blueprint for a modern computer. It's mechanical. It's really visionary stuff. It would have had conditional control-making decisions, basically. It had memory storage, and it read instructions from punch cards. A programmable mechanical computer. But what was it? Why didn't it happen? Was it just too complex for the time?
You nailed it. The ambition was huge, but the technology and, frankly, the money just weren't there in the 1830s. The level of precision needed for all those moving parts, they just couldn't manufacture it reliably or affordably back then. If you'd add, say, today's manufacturing tech and funding, we probably would have had computers, recognizable ones, almost 100 years earlier. It's a classic story, brilliant idea waiting for the world to catch up.
And working right alongside him was Ada Lovelace. She's amazing. Widely seen as the world's first computer programmer. She wrote an algorithm, a set of instructions to calculate Bernoulli numbers, specifically for Babbage's analytical engine. But she did more than that, didn't she? She saw the bigger picture. She wrote about concepts like beta analysis, looping, repeating instructions, memory addressing, stuff programmers use every day now.
It's pretty mind-blowing, isn't it? Thinking about looping, memory addresses, concepts core to coding today, being worked out by Lovelace nearly 2 centuries ago. It really makes you rethink where these fundamental ideas came from. She saw Babbage's machine, it wasn't just for numbers. She imagined it manipulating symbols, information, anything really.
And then we start seeing Babbage's ideas actually get built. Maybe not his full vision, but the inspiration takes hold. Late 1800s, Herman Hollerith, an American inventor. He designs one of the first really successful electromechanical machines, the census tabulator. This thing could read data from punch cards, U.S. Census data, and tally it up. Pretty quickly, too, handling up to 65 cards at once.
And it was a huge success.
Mm.
Massive. Hollerith started a company to sell these machines. That company eventually became IBM, International Business Machines. And it's helpful to picture how those punch cards worked. Basically, the machine tried to make electrical contact through the card. A hole meant a connection. Completing a circuit, registering as input, no hole, no connection. And the machine used to punch those holes. The key punch machine, that was essentially the first keyboard.
Okay, so the 1800s laid down the theory, started using machines for real work. But the period from, say, 1930 to 1950, that's when it feels like all the pieces just slammed together, the 20th century leap. 1936, Alan Turing comes along with his concept of a universal machine, the Turing machine. Just a theoretical idea, but profound. A machine capable of computing anything that is computable. Up till then, machines were built for specific jobs, right? Fixed tasks. Turing's idea is really the basis for our modern general-purpose computers.
At exactly the same time, 1936 again, over in Germany, Konrad Zuse actually builds the world's first programmable computer. It read instructions from punch tape, and crucially, it was the first to use relays with Boolean logic and binary code to make decisions. Boolean logic, just to remind everyone, is that simple true-false yes-no logic, or in binary 1 or 0. Zuse later used punch cards too for memory, and in 1942, his Z4 computer became the world's first commercial computer. Because of all that, many people actually point to Zuse as the inventor of the modern computer.
Wow, so much happening around the same time. And then, 1937, Howard Aiken at Harvard, working with IBM, starts on the Harvard Mark I, directly inspired by Babbage's analytical engine. And when you say machine, this was a machine, almost 1 million parts, over 500 miles of wire, weighed nearly 5 tons. And the speed, well, groundbreaking then, but puts things in perspective. 3 additions or subtractions a second, multiplication took 6 seconds, a logarithm. Maybe a minute.
And there's that great story from the Mark I team, Grace Hopper, one of the main programmers. She found the first actual computer bug, literally. A dead moth was stuck in one of the relays, blocking a signal.
No way.
Yeah, and she taped it into the logbook.
Oh, yeah.
That's apparently where we get the term debugging from.
That's fantastic. So we have these huge electromechanical machines, but then comes the rail shift, moving from clicking relays to silent, faster vacuum tubes. This is the start of modern computing, right?
Absolutely. That's the leap to digital electronics. Much faster, more reliable, well, sort of more reliable. And this brings us to a few key machines. First, the Atanasoff Berry computer, the ABC. Built by John Atanasoff and Clifford Berry between 1937 and 1942, this was the first purely digital computer. Used vacuum tubes, binary math, Boolean logic, really important foundational work. Then you have Colossus, built in Britain in 1943, with Alan Turing involved. Colossus was digital, yes, but also the first fully programmable digital computer. That programmability is key. Unlike some later machines, you could change its task relatively easily, which was vital for its job-breaking German codes.
Okay, so Colossus was programmable. What about ENAC? That's the one people often hear about. The Electrical Numerical Integrator and Computer, finished in 1946. Sounds like a beast. Nearly 18,000 vacuum tubes filled a whole room. It's considered the first successful high-speed electronic digital computer, but programmability was maybe harder there.
Exactly. ENIAC was incredibly powerful and fast for its time, a real milestone. But reprogramming it was a nightmare. You basically had to physically rewire parts of it for each new complex problem, not like loading software. While ENIAC was being built, though, another huge conceptual leap was happening. 1945, John von Neumann, a brilliant mathematician. He really clarified how computers should be organized, building on Turing's ideas. He formalized concepts like computer memory, how to address it, conditional jumps, subroutines, stuff Babbage had dreamt of mechanically. But his truly groundbreaking idea, that the instructions, the program itself, could be stored in the computer's memory right alongside the data, and that these instructions could be treated like data modified, changed, and should be coded in binary.
Ah, the stored program concept. That sounds like the missing piece. So the computer holds its own instructions in memory and can change them.
Precisely. That's the core of modern computing architecture. Von Neumann helped design ENIAC's successor, the EDVAC Electronic Discrete Variable Automatic Computer, finished around 1950. EDVAC was the first machine built from the ground up with this stored program concept. Much faster, too, over 1,000 instructions per second. That idea of storing the program in memory, that's what unlocked the whole computer revolution.
So EDVACI is really the ancestor of the machine you're using right now.
In architectural terms, absolutely. And just as a fascinating side note, von Neumann also explored the idea of self-replicating programs. So in a way, he's also the father of computer virology.
Wow. Okay, let's just pause and absorb that first half of the 1900s. Computing goes from being the sort of niche mechanical thing to a distinct field. We go from mechanical gears to electromechanical relays clicking away in milliseconds, then to digital vacuum tubes switching in microseconds. Binary goes from Leibniz's story to the actual language used for data, logic, instructions, programs. It really feels like this incredible accumulation. Abacus, Pascal, Leibniz, Babbage, Lovelace, Turing, Zuse, von Neumann, Hopper, Atanasoff, Berry, all these minds, these projects like Mark I, ENIAC, EDVACI, it really drives home that no single person invented the computer. It was this massive collective effort over, 5,000 years, but intensely concentrated between 1800 and 1950.
Absolutely. But even with vacuum tubes, there were huge practical problems that just begged for the next innovation. Think about ENIAC again, 18,000 tubes. They estimated about 50 tubes burned out every single day. You need teams of technicians just swapping tubes constantly. Plus, these machines were room size, weighed tons, and used as much power as a small town. Just not practical long term.
Right, sounds like a maintenance nightmare. But then, the breakthrough. The transistor. 1947, Bell Labs. First silicon transistor. This changes everything, doesn't it?
Absolutely game changer.
By 1954, you get the first fully transistorized digital computer, the Tradic. The specs are just astounding compared to ENIAC's. 800 transistors instead of 18,000 tubes. Tiny fraction of the size, 0.085 cubic meters versus 28. Used only 100 watts of power, and it could do 1 million operations per second. That's just a revolutionary leap in every single way.
And that transistor era also saw huge steps in hardware and software starting to mature. Hardware-wise, 1951, Jay Forrester comes up with magnetic core memory. Random access, the direct ancestor of RAM, crucial for speed. The 1957, IBM rolls out the first hard drive. You won't believe this. It weighed a ton, literally a ton, stored 5 megabytes.
5 megabytes, a ton.
Yep, and leasing it cost something like $27,000 a month in today's money.
Wow. That really highlights the scale of progress, doesn't it? A single photo on my phone is bigger than that ton of hardware could store. But the software side was exploding too, right? Especially once the hardware started getting a bit more standardized.
Exactly. Software innovation took off. 1949, you get assembly language. Not binary, but a sort of pseudo-English to talk to the machine. Still very low level, though. Then, 1954, John Backus at IBM creates Fortran, the first widely used high-level language. This was huge. High-level meant you didn't need to know the machine's intimate architecture quite so much. It was less error-prone, more accessible, made programming feasible for more people.
And Grace Hopper pops up again. She wasn't just about finding bugs.
Not at all. She was a software pioneer. In the early to mid-50s, she developed the first compiler. This was revolutionary for making programming practical. A compiler automatically translates that human-friendly high-level code, like Fortran, into the binary machine code the computer understands. It made the whole process faster, cheaper, almost instantaneous compared to doing it manually. She also helped out with COBOL later, another vital early language, especially for business.
So transistors, RAM, hard drives, high-level languages, compilers. The modern computing era is definitely taking shape.
It really is. But there was still a bottleneck. Even with transistors being small, you had to wire them all together individually. As computers got more complex, you had thousands, millions of transistors. That meant incredibly complex wiring, tons of solder points, lots of places for things to go wrong. Faulty connections were a major headache.
Okay, so how did they solve that?
The next huge leap, the integrated circuit,
Yeah.
the IC, or the chip. In 1958, Jack Kilby at Texas Instruments figured